which one is bigger from these two? Because size, and I am not talking about ionic size, yes? This is ionic size. Atomic size, this is the size of the atom. How does it increase? It increases this way, and it increases this way. So you expect the biggest element to be here, yes? Within the same, okay. Within the same period, you expect the biggest element to be here. Of course, the biggest element is here, yes?
Okay.
It increases as you go down, but as you are going across, which is what I have written there, yes? As you're going across. What happens is that this one and this one here has lost only one, and it was big to begin with. This one here gained 3. Now it gained size, but it lost 1, but they are comparable in size. A lot of the times, this one is bigger than that, okay? Because of that, I do not ask you that on the test. Is that clear? On the test, I either ask you about this, or I ask you about this. So which one is bigger? The one, which one is bigger? S2 minus, no, I put this the other way. S2 minus or O2 minus? Which one is bigger? S2 minus is bigger. Why is it bigger?
Because it's one down low.
Because it's low. Yes?
Lower, yes, lower.
Because it's low. Which one is bigger?
Which one's bigger? Nitrogen?
Nitrogen.
It's not called nitrogen. It's called nitrite, yes? This one is bigger because this has gained 3 pounds, yes? So I only give you the ones that you can tell which one is bigger from those two.
Potassium.
Potassium is bigger because it is lower in the periodic table. Is that clear?
Yes.
That's how I'm going to ask you this stuff. I will never ask you which one is bigger, this minus 3 or this plus 1. It's an unfair question. You kind of needed to memorize the whole thing for that to be true. Okay? Or have me explain all of it to you, which I am not. Okay? Yes? So that's the end of that one. We killed it. What else?
Are we going to go over the geometric signs?
The what?
The shapes? Geometric?
The shapes?
Yeah, right? Are we going to go over that?
Is that what you guys want to talk about next? Now let's talk about a little bit of those fluctuations in. Now, most of the time, when there is something that goes wrong in the periodic table, as far as electron configuration is concerned, when does that happen?
In the
Yeah, but when? When? Not where, but when?
Halfway and.
When we are either halfway or full way.
Or full.
The same thing happens for, let's say, ionization energy. What's ionization energy? What's, you don't know? Why not? Who's supposed to know, me? I'm not taking the class.
Probably.
Why don't you know? You didn't study this weekend? All right. Okay, ionization energy. The equation for ionization energy is, let's say, A in the gas. Now what? Does it have an electron added, or does it give an electron away? Do you take one from it? You take one from it. Okay, so ionization energy would look like this. Okay, ionization energy is when you have a neutral element and you take an electron from it, you ionize it, yes? That's called ionization energy. Do you expect this process to be exothermic or endothermic? Endothermic or exothermic?
Exothermic, no? You're taking away.
This process is going to be endothermic. You are taking something, someone takes money from you,
Okay.
that's good for you? You like that?
No.
Huh? Someone takes money from you, they're going to suffer the consequences, yes? Unless you like that type of thing, right? Okay, if the element had the electron, it doesn't want to get rid of it. Yes? If you take it from it, it's going to require energy. Okay? Because you are breaking attraction between the nucleus and the electron. Okay? If you take the electron from it, it's not going to like it. It's going to be positively charged. So that process is endothermic. So all of these numbers are going to have what sign?
Positive.
They're going to have positive signs. Okay? So, now there is something that happens in only two cases, okay? We're only worried about representative elements. Ionization energy, what did I tell you it was?
It's when it takes away an electron.
Increases this way and increases that way. So which are the elements that do not want to lose that electron? These electrons up here are the ones that do not want to lose that electron. Does this electron here care so much?
No.
No. This is a metal, and metals like to give away the electrons. So does it take a lot of energy for you to remove this electron? No. It actually wants to give it up, okay? I don't understand that. It wants to give it up, and there's plenty of those that are gonna take it. And these up here don't want to give it up. But once in a while, this is what happens. If we are at the representative elements, and this is the P area, okay? Now the elements that are halfway, they would end in what? In P what? Tell me. This is here, this is P1, this is P2. Guys, you know what this is?
Yeah, P3, yeah.
It looks like I'm talking here.
Chinese.
This is P4, P5,
P6.
and P6, yes? If you are in P3, what do you have? You have a P subshell that is what? Half filled. Because it is half filled, it is stable. Just like the D, right? When it's half filled, it is stable, and when it's completely filled, it is stable. So this for the P, does it want to lose that stability from being half filled? No, it doesn't. So when the ionization energy gets to here, what do you expect the number to be? You expect the number to be actually higher than this number here. Because here it is at P4. And what do you have at P4? This is what you have at P4. Yes? And does it like to be? Is this stable because it has 4 electrons? No. This electron here is being repelled by this electron here. So this ionization energy is lower than this ionization energy. So the trend does not apply when you get to this, to the P3. Yes?
Okay.
Hello? So the ionization, okay. Take home messages. Ionization energy for those that end in P3 is greater than those that end in P4. Not all the time, once in a while. But you expect that because?
Because it wants to gain those other electrons.
It's more stable than P4.
No, gain, no. This is losing it.
It's more stable.
Because it is half filled, it doesn't want to lose it, okay? But this wants to lose it because of electron-electron repulsion. So when it has 4, it wants to be what? It wants to be 3. Now how about this electron configuration here? What do you think? Does that want to lose it?
No.
No. That one does not want to lose it because it is?
Completely filled.
Because it is completely filled. So you expect this to have the highest ionization energy. Okay? Yes? Yep. So if we're talking about electron affinity, this is electron affinity. What's electron affinity? Hello?
Gain energy.
Gain an electron, yes?
It's a plus.
So-
Plus electron.
this is going to gain an electron. Because it is gaining an electron, these numbers will be what? Endothermic or exothermic? Exothermic. Because the last one was endothermic, this has to be exothermic. So these numbers are negative. And these numbers, as you read them in the periodic table, increase this way and this way. So give me an example. If this is minus 100, 1 to the right-hand side of that is supposed to be what? Give me an example. Minus what?
Minus 99.
No, minus 99.
No, minus 110.
Okay, you are right, but you're not. It would be minus 115. But this 115 is a smaller number mathematically, yes or no?
Yes.
It is a smaller number mathematically, so he would be right. Smaller number mathematically. But this is a bigger release of energy, yes or no?
Yeah.
What releases more energy, 115 kilojoules or 100 kilojoules? 115 kilojoules is more energy released. Okay? So when I took the class, I had a problem with that. I'm like, how can they say this is increasing this way and this number is getting smaller? It's not increasing, right? But it is increasing in the amount of energy that is released. This amount of energy released is bigger than that. Okay? Yes or no?
Yeah.
Yes.
So, when do you see gaps in this electron affinity? When do you see gaps? Or when do you see a little bit of the deviation from what you expect? You see them at
In the middle?
P3 and P6.
It's the
Yes?
same expression.
The same exact thing.
Same thing.
So what happens when you are at P3? This is P3, yes? When you are at P3, does it want to gain another electron?
No.
It does not want to gain another electron. It does not want to gain one, because if it gains one, what
It's
happens?
going to be unstable.
It's going to be like this.
Right.
And it doesn't like to be this way because of electron-electron repulsion. So it doesn't like it. So at P3, the electron affinity should be what type of number? Okay, does it like it? Does it like it for you to add that electron to it, yes or no? It does not. It does not like it. So you kind of have to force it. So sometimes these here they are less exothermic, or they are even endothermic. Okay? So at P3, they are less exothermic, because the addition of an electron will create electron-electron repulsion. Okay? Yes? And if you look, I mean, I have the slides, yes? Okay, I'm going to tell you. Here is the electron affinity. The electron affinity for carbon is minus 122. No, you don't need to write this down. You just need to open your ears. The electron affinity for carbon is minus 122. Electron affinity for nitrogen, do you expect it to be what type of number in comparison to carbon?
120.
Less negative, yes?
Yeah.
So it should be, it's about 7. Positive 7. So did nitrogen like for you to give it an electron? No, it does not. Because if you give an electron to nitrogen, it becomes like this. It doesn't like it. Now the other one, past P4, which is P5, if it gains an electron, then what? Then says this, if it gains an electron, well, It's working its way almost to be full, yes? But it doesn't mind that much. So the electron affinity for oxygen is minus 141. And that is increasing that way, yes? It is increasing that way except when you get to what point?
Fluorine.
When you get to,
P3 or P6?
well, yeah, when you get to P3, but P6, but the first one was when? First problem was at P3, yes?
Yeah.
So, fluorine is minus 328. Okay, that's a big number, yes?
Yep.
And then there comes the noble gases, which is group 8A. Okay, and the noble gases, what do you expect? To be like P3 again. It doesn't like it. So they have endothermic electron affinities, okay? Yes?
Yep.
So normally, this is how it is, yes or no? You can expect oxygen to have what type of electron affinity compared to fluorine? This one is bigger or lower? Electron
Lower.
affinity.
It's lower.
Lower electron affinity. When you get here to nitrogen, then what do you expect this to be?
Higher.
Higher.
Is this one more exothermic than this one?
No.
No. This one is not. This one is not more exothermic than this one. This one, in fact, is more endothermic than this one. So here, it is increasing that way, yes?
Yeah.
Except when you are nitrogen and you are at the noble gases, in which they become more endothermic. Guys, yes or no? That happens for ionization energy, and what else does it happen for?
Electron.
Electron affinity.
Professor, what's the sample question on like on a test that you would give something like that on the test?
Well, something like this, normally when I ask you which one has a higher electron affinity, I expect you to know this trend only.
Okay.
This is what I expect you to know, that electron affinity increases that way. But if I tell you, hey, the electron affinity of nitrogen is, let's say, 7 kilojoules per mole, and the electron affinity of carbon is minus 122, how can you explain this? Then your explanation would be, because the elements gain stability by being either half-filled, by having the subshell either half-filled or completely filled. So this element has a half-filled P subshell, yes?
Yeah.
So, does it want to gain an electron? No.
No.
Does it want to lose an electron?
No.
No. So this has abnormal from the trend, ionization energy and electron affinity.
Okay.
Okay? If it's ionization energy, then it's higher than the one on that side. If it is electron affinity, it's more endothermic than the ones on the sides of that. Okay? Yes or no? Is that difficult? Is that difficult to understand? Hello?
No, those are just exceptions.
Yeah, it's kind of exceptions to the rules.
Exactly.
Before, just remember about R.
Guys, is that clear for everybody?
Yeah.
So at that point, the group would be endothermic.
Well, I'm not saying it's endothermic, I'm saying it's more
More
endothermic, because I want you to think about it the right way.
okay.
Because if I tell you it's more positive, then you're like, what do you mean?
More.
So more endothermic. It requires more energy for you to add it than the one next to it. Okay? Now, group 1 from the periodic table is called alkali, yes? Did we talk about this before?
No.
Group 1 from the periodic table is called alkali metals. And they react with water violently. Okay? Reactivity increases as you go down in the periodic table. So for example, potassium will react with water. Most of the time explosively,
Cool.
to form potassium hydroxide and hydrogen gas. That is how most of those metals react. So the pure metal will react with water to form hydrogen gas and the hydroxide. Okay? That's for the alkali metals. That's group 1. Group 2 is called alkaline earth metals. Alkaline earth metals. They react with water, but to a lower extent, okay? Once again, reactivity increases as you go down in the periodic table. Reactivity with water. Like for example, beryllium does not like to react with water at all. But that's the first one, yes? On that group. As you go down, they start reacting and reacting. You gotta heat the second one, and then the third you don't have to heat. Okay? But potassium is totally out of control, yes? You put potassium in water, and you are going to see an explosion. The next group I'm interested in you learning is the halogens, and the halogens is group 7A. Is this 7?
Yeah.
That's 7.
What?
Group 7A is called halogens. The halogens naturally occur as diatomic molecules. Most of them are gases at room temperature except for bromine, Br2. So normally, halogens are diatomic and they are gases. And they're colored gases. Okay? That's how they exist at room temperature. Now, do we have any metals in their, any group 1 cation in their metallic form in the environment? No. In the environment, these have either reacted with water or they have reacted with oxygen to form the metal oxide. Okay? So, if these group 1 or group 2 metals react with oxygen, what do they form?
Oxide.
Metal oxide, yes? So, is that a metal oxide? That is a metal oxide. Is it the right amount of potassiums to oxygens? No, oxygen has what type of charge? -2. And this is +1, so this is like that. That is the metal oxide of potassium, yes? Yes or no?
Yes.
Most of them are found in the environment as the metal oxide or as the hydroxide or the whatever else, but they are not from the periodic table with an electron to donate. Okay? Last one is 8A. 8A are the noble gases, yes? The noble gases, like the noble steed from Shrek. Yes?
Donkey.
The noble gases do not make compounds, yes? They do not like to mix with others. That's why they're noble. If you don't like anybody, you should be royalty. So noble gases in general do not make compounds, okay? And that's a little bit of a lie, but that's okay. Xenon forms compounds. Xenon fluoride. Nasty business. Okay? So noble gases are inert. Everyone wants to have what type of noble gas, what type of configuration?
The noble gas
configuration. So when we do electron configuration, there are some configurations that are isoelectronic. Isoelectronic means they have the same configuration. Most of the time, it will be the configuration of a noble gas. So this is the configuration of ions, yes? Tell me, what is the noble gas configuration of, let's say, neon? Guys, neon.
What's the?
Neon has, how many electrons does neon have? You need a periodic table, yes? I don't have one.
Yeah.
I don't memorize a periodic table, you should.
10.
10 what?
Electrons.
1s2,
Oh.
2s2, 2p6. Is that complete? Is that 10 electrons?
Yes.
This is for neon. 10 electrons, yes?
Yeah.
That is neutral for neon. Now, fluorine would form what type of charge?
Minus?
Same.
-1, yes? -1. So let's do the noble gas configuration for this. Fluorine normally has how many electrons?
9.
Look at the periodic table. It has 9 electrons. But it has 1 extra, yes?
Yeah.
So this is plus another electron. How many electrons is this? 10 electrons. We'll have the same gas, same electron configuration as
Neon.
the noble gas neon. So what is it going to look like? 1s2, 2s2, 2p6. So neon and F minus are isoelectronic. Yes or no?
Because of the minus, right?
Yeah.
Because there is gaining.
So give me the electron configuration for potassium. And give me what noble gas configuration that will be isoelectronic with.
Argon.
Give me another 2. Actually, give me 3. How about that?
Okay.
Right. It's potassium plus, yes?
Yeah.
Write the electron configuration for this and provide 3 examples
Neon.
of other elements that are isoelectronic to that. What time is this class finished?
No, sorry.
You are enjoying the speed?
Gotta do what you gotta do.
Unfortunately, that's what happens when you take your time and other things.
I'm impressed.
What are you impressed of? You know,
She just told me shut up, so I can't go. I'm impressed. Really? I'm not lying, really. Lying.
Violeta, did you do it?
Listen, she tried to remember your name. But, oh God, it's Violeta.
No, I don't have to think that much. My processor is the latest Intel Pentium.
Really? I'm impressed.
You should be.
Give me some of that, bud.
Okay, guys, let's do it. You guys are taking too long, and this girl here is texting. You're not texting? I'm gonna look in your phone right now. If I see a text that you just sent, I'm gonna give you an F.
Look, I haven't even opened my phone.
So you were checking the time because it's taking too long, the class? Even worse. So tell me the electron configuration for potassium plus.
1s2, 2s2, 2p6,
2p6, 2s2, 3p6, 4s1.
Okay, everybody got that?
Yes.
Outstanding. What did she say after 2P?
2p6,
3s2,
3s2,
3P?
3s2.
Technically, it's not.
3p6, 4s1.
3p6. Yeah,
And then,
4s1.
how many electrons does this thing have?
it gives up one. It's losing an electron.
No, no, it's okay, it's okay. Let's relax, you'll enjoy it better if you're relaxed, okay? So, this is the electron configuration for potassium. Potassium has how many electrons?
19.
19 electrons. Potassium has 19 electrons. How many electrons are here? There's 10, and here is 18, and that's 19. Yes or no?
Yes.
Now, you have to notice at this point that you were not trying to find the electron configuration for potassium.
Yes.
You were trying to find it for potassium plus. Potassium plus has lost how many electrons? One electron. So it will be 18 electrons. So it lost 1 electron. Which electron is the one that it lost? It lost this one. Okay, so since that doesn't have any electrons, let's erase it. You can just put 4s, it had it, and now it's gone. Okay, it likes to lose it. Because it wants to have a noble gas configuration. And it lost the outermost electron, and now it has a noble gas configuration. Yes or no?
Yes.
Outstanding. What other noble gas, what's the noble gas configuration that has the same electron configuration? Argon. Argon has how many electrons?
18.
Argon has 18 electrons. Which one is the other noble gas configuration that has the same, that is isoelectronic to this?
Fluorine.
Chlorine?
Chlorine
Cl?
minus.
Cl?
Minus.
Outstanding.
Minus.
Oh, Cl minus.
Minus,
More
minus, yeah.
outstanding.
Minus.
Cl has how many electrons normally?
7.
17. But since it has this one, it gains one more to become 18 electrons. So it has that same noble gas configuration. Which other element? You got 2. We need a 3, yes? Which other one?
Sulfur? 2 minus. Sulfur
Okay,
2 minus.
calcium 2 plus will do it.
Okay.
What else? No, we can have more.
Sulfur 2 minus.
And sulfur 2 minus. Okay? They will all have the same noble gas configuration. Yes? Is that clear? Very good. I forgot to talk about ionization energy, didn't I? Did I? Yes, I did.
Yeah, we started.
You talked about it already. The one with the exceptions.
That's the first one.
The one with the
Really?
P3 and P6.
Half full.
Yeah. They're exothermic.
I guess my processor is not the latest after all.
No, Pentium is having a hard time.
Go Intel.
All right.
Update.
So, we're still talking about ionization energies, okay? I was just tripping, and I didn't finish the other topic. Okay, we're talking about ionization energy 1, ionization energy 2. Ionization energy 1 means for losing the first electron. Ionization energy 2 means for losing the second electron. Ionization energy is for losing the third electron. Okay? Yes or no? Very nice. So let's say I have this noble gas configuration. 1s2, 2s2, 2p3. Let's not say 2p. Let's start like this. Let's say I have this noble gas configuration. Which are the outer core or valence electrons there? 2s2. This is the outermost shell and has how many valence electrons? 2. This is an element in what group of the periodic table? In group 2 of the periodic table. Now, what are these electrons here called?
The inner.
They're called inner core electrons, okay? The first ionization energy is for losing the first electron. That ionization energy, as you remember, is always what? It is always smaller than the second ionization energy. and that eventually is smaller than the third. So it is always easier to lose one electron than it is to lose two, and that becomes more difficult than to lose three. Yes? Hello?
Yes.
So first ionization energy, it is always a smaller number than the second ionization energy. But there is a jump in ionization energy from the valence electrons to the inner core electrons. So let's say this ionization energy might be, okay, let's do another. How many ionization energies can this have? You can have 4, yes? Because you can take every single one of these electrons. This first ionization energy is supposed to be a number that is lower or higher than the second?
Lower.
Lower than the second. How about the third ionization energy?
Higher.
It no longer has electrons that are valence. Now you got to take it from inner core. When you are taking electrons from the inner core, it is a big, big difference. Like 5,000, 10,000, 15,000, 20,000 kilojoules of a difference. So let's say that the first ionization energy is 700, and the second ionization energy is 1,000. And you take the third, of course this is a made up example, yes? You take the third, what number do you expect?
Greater than 1,000.
Yeah, but give me like, what do you think? I mean,
5,000.
this is increasing by 300,
Yeah,
yes?
so what's
Right.
up there?
The other one, if it's 1,300, is not inner core. But this one would be like something like 3,000. When you see this jump, it was progressively going higher and higher at a certain speed. And then you see this huge gap, or this huge jump. Whenever you see that big jump, is because it went from where to where? From the outer core to the inner core. Okay? You can say from the valence electrons to the inner core electrons. Okay? I'm going to read you some numbers now. And I'm going to tell you how this is going to be a question on the test. If I can find it. Okay. So I'm going to give you numbers, and you tell me where this element is. Okay? 786 is the first ionization energy. No, you don't, guys, please. You writing this down? Don't write it down, just look here. 786, first ionization energy. Second ionization energy, 1577. Third ionization energy, 3232. So far it's increasing by how much? 786,
Twice.
1,500
It doubles.
to 3,000.
It doubles.
It's so far doubling. And then 3,000 to 4,356. And then it goes to 16,000.
That's when it gets in.
Would you consider that a big gap?
Yeah.
How many valence electrons does that element have?
Yeah, it
It has 4
It has
valence
4.
electrons.
Okay, I'm gonna repeat the numbers to you,
4,
okay?
no?
Don't write them down. Ready? 786, 1577, 3232, 4356, 16,000.
4 valence electrons.
It has 4 valence electrons. I gave you 4 numbers that were close. So this is an element that has 4 valence electrons. What group is this element in?
In group 4.
In group 4, which is members of which element on the top? Elements of carbon. Okay? It is a member of that group 4. Okay? Outstanding. I'm going to give you another one. You ready? 578, 1817, 2745, 11,577.
3.
3 valence electrons. Okay? This is a member of what group?
Group 3.
Group 3.
3 of the periodic table.
Outstanding.
Wow. You guys take my breath away. Okay, I'm gonna let you have another one, okay? First ionization energy, 1,000. Second, 2,000. Third, 3,000. Fourth, 4,000. 5, 7,000. 6, 8,000. 7, 27,000.
6.
So on the 7th, I saw a big jump, must have had 6. This is a member of what group? Of group 6. This is a member of oxygen. Okay? How do you like that? Hello?
Yes.
You like that?
That's gonna be a question on the test, bro? Something like that?
Yes, that could
something
be.
like that?
Could be a question on the
How do you
test.
know? How do you know? Because it's like a trend, and then if it jumps up like that, rapidly like that, then the previous number, then it stops there. Like,
You want me to write them on the board?
Yeah.
yeah, just
Would help you?
resolution.
I have them, I just don't understand how you see 3 or 6.
All right, I'm gonna write them on the board, okay? Let's clarify it for those of you that are tripping. I am not even telling you what element this is, yes? 786. Wow. Right. I looked at it and I wrote something else. 1577.
Okay, you see right here?
What do you expect the ionization energy to do? As you start taking electrons, the element starts doing what? Disliking it, yes? So this is ionization 1, 2, 3, 4, and 5, yes? So this ionization energy, you look at it, and you say, okay, 786, that tells you nothing. You go to the next one and you go, okay, that increased by about, okay, whatever, it's doubled. And then you go here, 15 and then 32, that's like, once again, double. And then here, 32 on that, well, that's not so double, but still not a large increase. And then you go here and you go, damn, what happened? It was increasing by double, but this is not double of that.
It's 4.
How much is this?
4.
That's like 4 times. Okay, from 4,000 to 16,000. That's a lot of money, if you're talking about money, yes? So what happened here? It went from outer shell electrons to inner core electrons, because inner core electrons are more difficult to remove. Okay? Yes?
Yes.
Is that clear now? How can this be a question on the test? I can give you the little picture like this with numbers and tell you this is a member of what group in the periodic table. Okay? Yes? Or I can ask you, ionization energy increases from left to right. But if you have, for the same element, ionization energy for the first electron is always what compared to the second? Is always smaller. Meaning that it becomes more and more difficult to do what? To remove that electron. As you start removing electrons, this thing does not want to have that many charges. Yes? So you always expect ionization energy 4 to be lower than which ionization energy?
5.
Why you guys freeze?
Okay, so the reason why you put like 4 electrons, balanced electrons, was because the ionization.
Yeah, because it happens on the 4. All right, guys, let's move on, okay? Write this down. This is called dictation. Do you like dictation? Machina.
I do.
Outstanding. Now, metals are soft, shiny, and conduct electricity. That happens as the more metallic it becomes, the more of those characteristics. So which one is softer and shinier? Sodium or carbon? Sodium is softer and it is shinier and it conducts electricity better and heat better. So conduct electricity and heat. All metals do that. The more metallic, the more of that they do. Have you ever cut a metal with a knife?
Cut the metal with a knife.
You never cut a metal with a knife?
Yeah.
I'm pretty sure you have never seen this. But let's say I have a piece of metal that big. I have a piece of metal this big. You can cut that with a knife like that, from the top to the bottom, as if it were butter. That is because metals are soft. Now, which metals can you do this? You're not used to seeing them, but this is sodium and potassium. They have to be swimming in oil, because if you expose them to the air where there is water, what happens?
They're hardened.
They catch on fire. Okay? Okay? A little fire, no big deal. I always thought of, in the Saw movie, putting a little bit of potassium inside of those capsules. You seen the capsules? Put a little bit of potassium in there in oil, and then tell the person, hey, blue pill or green pill? And then they take one. When that potassium gets to the stomach, the HCl will dissolve the cap, and then it will explode. So basically, there's no
This guy's sicker than
insides.
Saw, bro.
You're looking down, and all you see is your outstanding. That would be nice.
Garcia Saw.
I would do it to you. If you cheat on the test, that's what I'm going to do to you. I'm going to tie you down and record you with that stuff. Hey, take the blue pill. Both pills are going to have the potassium inside. All right.
What happens if you eat bananas with water?
No, the potassium I'm talking about is potassium. The potassium in a banana is not potassium, it's potassium ion. Okay? Potassium I'm talking about is the metal from the periodic table with a 1 electron.
Everybody would explode already.
Now, yeah, no, it's a good question, okay? Because most people just call this thing potassium, yes? This, you gotta make this. Because this already gave the electron to whoever to become this. There's none of this in the environment. You gotta pass electricity through potassium chloride to make this potassium metal, okay? So, yeah, banana has this. The banana is radioactive though, releasing gamma radiation inside of your body. Don't worry, it's giving you cancer. You like bananas, don't you? That's cool. You keep eating it, man. It's everywhere. Okay. All right. Let's continue. So what I say, metals
Are soft, shiny, and
soft, shiny, conduct electricity and heat very well. Yes. Now non-metals are brittle. Do not conduct electricity. So obviously the total opposite of the other stuff, yes? Do not conduct electricity, do not conduct heat very well. And the metalloids do what? The metalloids are like a little bit of both, okay? And the metalloids are which one in the periodic table? I think I already talked about this before. Now what I want to tell you is the non-metal oxides, okay? Non-metal oxides react with water at times, or most of the time, to form acids. Non-metal oxides react with water, sometimes with sodium hydroxide, to make acids or bases. Acids or bases? Yeah, because I said sodium hydroxide. But metal oxides in general react with water to form acids. They react with sodium hydroxide to form bases. Metal oxides. I mean non-metal oxides. Did I say metal oxides? Hold on a second.
You said non-metal oxides.
Non-metal oxides. I just said metal for some reason, just to confuse you, okay?
With water or sodium hydroxide.
So, sulfur dioxide, okay? Sulfur dioxide is an oxide of sulfur, yes? Sulfur dioxide will react with water to make
Sulfuric.
an acid, okay? Most of the time either sulfuric acid or sulfurous acid. So, picture this. Look here. SO2 plus H2O. Tell me, if you combine those, what are you going to get? H2, SO, SO3, yes? Yep. You see it or no? Okay, so most of those oxides will form acids with water. If they were with this, for example, what would it form? What acid would it form?
But yeah, but hold on, but with hydroxide or with water?
With water.
With water, carbonic acid.
It will form, that plus this gives you H2, one carbon, how many oxygens?
CO3.
3, carbonic acid. Okay? By the way, most of the time, those metals that are very hard to you, they're not the pure metal. Those metals, like this metal, they're alloys. So they got other things in it making them harder. Look, let's do something. Let's talk about, next thing we're going to talk about is, let's talk about Lewis dot structures. Okay, and then we go into molecular shapes. When do you guys have a test? Next week? You want one next week?
Next Monday.
Next Monday?
Yeah, next month.
How about last Friday? You want one last Friday?
It's even better.
Yes, we already got A's
It's
on.
even better.
Okay, Lewis dot structure. Lewis dot structure. Okay. The Lewis dot structure depends on the number of valence electrons, yes? Carbon has how many valence electrons?
4.
4. I am going to place in an imaginary box. You see why it's imaginary? It's there now, and then you delete it. It's not a box, it is a square, yes? And on each side of this square, you can place a maximum of 2. Yes, but when I place the first one there and I go to place the second one, am I going to place it here?
No.
No, right? As you might have imagined, there is electron-electron repulsion from whose rule? Pauli? Aufbau? Whose rule? It's not Pauli, it's exclusion principle. This is Hund's rule. Hund's rule says that the next electron will go on the next side. There it goes. And the next one will go here. So it has 4. That is the Lewis dot structure for carbon. And what is it for silicon? Somebody's favorite element. Silicon. Still 4, yes?
Yes.
So they all look the same. It's like you don't have to practice this. How many does oxygen have?
6.
6 valence electrons. Here's the first one. The second one, here. Third here. Fourth, 5, and 6.
That's it.
Now, if you do it like this, it's still okay. It's the same thing, yes?
Right.
It's the same thing. Every group underneath the oxygen is the same. You go. if we are going to find the Lewis dot structure, because this is so simple, it's not gonna be on the test. Okay, that's how simple this is, but you have to learn it. Actually, it might be in the ACS test. The ACS test is key. Right? So, let's say I want this. Carbon with 4 chlorines on it. I want the Lewis dot structure for carbon with fluorine, whatever you get. This is how you do it. You gotta measure, or you gotta count the number of valence electrons for carbon. How many?
4.
There's 4.
How many for chlorine?
7.
Hello? Where's chlorine at?
Chlorine
Group
is
7.
Yeah.
How many are there?
7.
No, what do you mean 7?
No, there's
It
1.
has 7 electrons.
There's
That's
one.
the
There's
valence.
4.
There's,
How many chlorines are there?
28.
there's 4.
What do you mean
It's
28?
4.
There is 4,
I
so
just told you.
times 4. 7 times 4 is 28 electrons. And you add this number plus that number, it is 32. So when you are doing the Lewis dot structure, you have to add the number of valence electrons. Okay, 28 to her. And you are going to choose a central atom. Central atom is the one that makes the more bonds. Which one makes more bonds? Carbon or chlorine? Chlorine makes how many bonds? 1 bond because it accepts how many electrons? 1 electron. Carbon makes 4 bonds, so it's going to be the central atom. I'm going to make single bonds to everybody else. And I am going to put the other element I have as single bonds to those, Cl, 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 and Cl. I'm going to go to the elements outside, and I am going to complete the octet for those elements outside. Not the central one. Central one is to the end. So, how many electrons does this have right now?
2.
It has 2. I gotta make it 8. And now I count the number of electrons I have here. How many do I have here? Here. No, 2.
2.
And those 6 is?
8.
8, 8, and 8. How many is that? 32. So that is the Lewis dot structure, and the bonding electrons are lines. Yes? Bonding electrons were lines. Yes, that is covalent bonds. Okay? Don't worry about that yet, okay? I just want to show you this now. Wait, who it for NH3?
Yeah, actual line with 1 electron or it's 2 electrons?
1 electron, I mean 2 electrons, yeah. 1 bond, 2 electrons.
What's up with the line? I think of that confusion.
The line is a way to denote 2 electrons.
Okay, but where is
Sharing
where does those 2 electrons come from? This isn't.
They came from the carbon and the chlorine. They're sharing them. I haven't talked about this yet. Just learn how to draw. What do you do first?
The central is M.
No. First thing you
Count
do,
the electrons.
valence electrons. Nitrogen, how many? 5. Hydrogen, how many? 1
times 3.
times 3 is 3, and this is 8. I choose a central atom, which is nitrogen. I make single bonds to everybody else. Single bonds is denoted by a line. I have 3 hydrogens. How many lines? 3 lines, and I put the hydrogens here. Okay? I have to fulfill the octet rule for the ones that are outside. Yes? For these. Now, does the octet rule apply to this? Is it 8?
No.
It's not 8, it's hydrogen.
1.
Hydrogen does not have 8 to have a noble gas configuration. Hydrogen only needs 2. So that hydrogen is happy. 2 electrons. I gotta count. How many? 2, 4, and 6. There are 6 electrons there. Okay? How many do I need? I need 8. I need 2 more. I am going to place them in the central atom. Yes?
Isn't the central atom the one that's supposed to be further from having a full 8 electrons?
The one that makes the most bonds, that's the one you're gonna make the central atom. And don't worry about anything else. Okay, how about this? Let's do this one. Do that one, my friends. What time is this class over? 10 minutes?
No.
Now?
No.
You're lying. It's over? It's never over for me. Starting.
So it's 14?
I don't know. How many guys, why are you packing up? How many valence electrons for hydrogen? 1. How many valence electrons for oxygen? 6. How many valence electrons for chlorine? 7. If you add all this business up, what does it give you? 14. Which one is the one that makes more bonds here? Oxygen makes more bonds, so oxygen will be central atom. I am going to place single bonds to the other 2 elements, hydrogen on one side, chlorine on the other side. I'm going to complete the octet for the ones outside. Hydrogen is already complete, yes?
Yes.
Now I go to chlorine. 1, 2, 3, 4, 5, 6. 2, 4, 6, and those 2 are 8.
8,
And here is how many?
yeah.
2.
2. So 8 plus 2 gives me
10.
10 electrons. I need how many? 14. I am going to place these other 4 electrons where?
On top.
In the central atom. Okay, there you go. 1, 2, 3, 4.
What if they repel each other?
They would. Okay, guys.